what I'm going to talk about in the first bit this morning is really just some of the basic ideas in system design that lead to people building systems like speculation to speed up programs. But this is a very high level, so it's quite so if you're not a if you're not a sort of real hacker programmer, don't worry, this is going to be a very high level general principles. The second bit, I'll probably take a few minute coffee break in the middle. The second bit really will be a detailed dive into how we provide secure enclaves for cloud computing so that people can run their data processing in the large, but can do it without fear of certain threats of loss of privacy, confidentiality of data, modulo Spectre and Meltdown. So anyway, but that's the second part. So it's quite a different level of detail. So credit for slides. The first set of slides are due to a friend of mine who's a professor at Waterloo University, Keshav. Waterloo's a jolly good university in Canada, near Toronto, where interesting things came out of there. You may remember a thing called the BlackBerry that was started by people out of Waterloo. And they do lots of cool stuff with electric vehicles and charging schedules and so on, which were quite interesting for the Turing. In fact, he was here last year for a brief visit. So I've got his slides with permission. They're actually freely available. He makes all of his materials available, which is really good. And the second set of slides for the second talk are from my colleague Peter Pitzuk at Imperial College, who we work with here on this secure enclave work. Okay, so enough sort of background and admin. So basically, I'm just going to go through a few general principles of system design, which come from my perspective, where most of my work for the last 30 years has been in networking, but we could be talking about application performance or operating system performance or database performance, so the same kind of basic principles work. Basically, system design is a weird mix of engineering, science, and art, because you need to understand a sort of holistic view of all the things going on. It's not just something you can say, we will optimize this thing. What will you optimize it for? Right? Will you optimize it for throughput or latency or for memory footprint or whatever else you might be thinking about? So a given system will be designed, hopefully, by people that have made some trade-offs. They made some decisions about some properties, and they really care that they get that trade-off in the direction that's, that's what the user or the customer needs most. So extracting the most from what you have is kind of a, it's not a trivial problem. And why is this relevant to data science, machine learning, and AI? Well, because a lot of what we do in the Turing and other places that do this kind of work involves a lot of data and a lot of processing. And so if you're bottlenecked in the wrong place, then you may have tasks that never finish in a reasonable amount of time, or you may use up all your credit on Azure or AWS or whatever cloud service you're using. So you actually care about this. And quite small changes in trade-offs can lead to very large performance shifts. So you can be looking at 10 or 100x performance changes just by getting something slightly wrong. And these are kind of well-known things, but you're staring at some problem and it's just not finishing, and then you try a much smaller data set and it finishes in some amount of time, and then you scale it up a bit and you measure the system and you see, oh, okay, we're scaling in memory badly, so we're exceeding the memory system, the physical memory bounds, and then we're hitting some other performance limit like paging or some other thing that has massively lower performance, that's way worse. And there could be other things like a very simple example, which we'll talk about in the second part of the talk, is the difference between Hadoop MapReduce and Spark MapReduce is the use of RDDs means that data is not retrieved off of storage every time you apply a function to some stored data. It's actually distributed, replicated, and then accessed locally, and that local access is obviously massively faster. And if you're familiar with a lot of data center systems routinely use systems like Memcached, which is another tool for doing performance speed up. So you avoid going out to larger capacity but much slower, much higher latency devices like spinning disks. Okay, so that's kind of what we're interested in, and there's a bunch of resources you have to care about. So in any system, there's some performance bottleneck. And we've been working with people in developing countries, and you might laugh at 28.8 kilobit modem. I mean, this is a thing where if you're sat in, Southeast Asia, in the middle of nowhere, or half of Africa, or a lot of South America, that might be as good as you get. You might be using maybe not a modem you think, but you're actually using a GSM phone. because there's no data coverage, or you're using a 2.5G edge phone and you've got a few kilobits. But you might have gone there, maybe you're a veterinary researcher from Royal Veterinary College looking at giant cats in Kenya or whatever, and you've got this fantastic laptop you bought on your research grant, but your bandwidth is not great. So, there's a constraint there, and a constraint is something you're not probably used to if you've arrived in that world and you've got that constraint, where normally you plug in your laptop and you've got 55 megabit Wi-Fi or gigabit Ethernet or 10 gigabit Ethernet, and suddenly this constraint shows up. And you care about what you do. So for a simple example of what we would do in that world is, if you're going to give a village a bunch of laptops, you can put the whole of Wikipedia on USB storage, the whole thing. So they don't go and use the net to access it. It's all copied locally once, and it just arrives on the disk already. Okay. So identifying where the constraints are and then figuring out what you might do like that, of course, then you don't get the updates unless you use a network, but updates are much smaller than the whole data, is important. And there are other places this shows up, and there are people in the Turing who worry about data-driven engineering design. So for example, if you're designing cars and you want to maximize reliability and mileage or fuel efficiency, but you've got a cost constraint. You want to hit a particular segment of the market. You're not Elon Musk with an arbitrary amount of money to put a spare car in space. You want to build the car for 10,000, not 50,000. Can you get the thing to be super reliable and super efficient? And maybe you can, but maybe it then is very small. Right? If you look at cars that people have done that for, I guess Nissan Leaf would be an example of quite good electric car mileage, but pretty tiny. Of course, you can't always quantify everything, and this is part of the system design art, because you need to kind of make guesstimates, or you need to have some idea about what you would like to happen. So there are a whole bunch of, some people call these the illities of system design: scalability, modularity, extensibility, even elegance. These are pretty hard to exactly quantify. They're hard things to kind of nail down. Scalability, we could come up with numbers. I mean, scaling in computer science does sort of have the idea of complexity of a system. What's the big O order of the system in terms of number of messages or amount of memory or number of cycles of a CPU to do one iteration or whatever. So that would be some definition, but it's not as simple as that when you have a distributed system where there's trade-offs between locality and remote access, which you can make just different decisions, and then your scaling will change. Why the cloud is out there, why cloud computing is out there, is that the performance of data centers hit a certain sweet spot in scaling in terms of the CPU and storage costs and the network connectivity within a data center. But it actually has a different downside, which is you have to get all your data, if you keep all your personal data in the cloud, remotely from your phone or from your home. And so that's a trade-off, where you could keep all your data at home, but then you would lose out on the scalability of, for example, reliability. Home computer is probably not as crazy reliable as a highly replicated system in a data center or multiple data centers. On the other hand, this is not this is a moving target. It's not a fixed problem. So technology changes. We know all this, but I'm just going through. These are all factors when you're designing a system. Things come along and change. What's a big change at the moment is that we're moving to many cores. We've been doing that for a few years, but we're really moving to really large numbers of cores. So some of you might be using machine learning that's running not on the main CPU, but it's running on a GPU, which might have 600 cores. And if you were a normal regular programmer, you might have a laptop that has 4 cores, or you might have a desktop or system down in the basement that has 16 or 32 or 64 core. But 600, 800 is a big number for one unit. And there are systems coming along that are way more than that. And that's one technology shift, changes the way you program, quite a different paradigm. Other technology shifts are in favor of solid state storage versus spinning disks. Spinning disks have necessarily got moving parts, so reliability may not be so great, you may think, and latency will be higher if your head's not above the data. Throughput might be higher. You might be able to get data streaming data off a disk very fast. But actually, SSD are not necessarily reliable. It depends how you duty cycle the writes. If you write data a lot, you're looking at actually quite a limited lifetime. There's only a certain number of writes you can take in the technology they have. Market conditions can change, obviously. The world can shift. One example might be the cost of electricity could change. If you're running something that's energy expensive, computation in a data center uses a lot of energy. I think currently people are saying data centers are getting more, the power usage efficiency of data centers is getting better. Certainly, we've probably maxed out the efficiency, battery life of phones and laptops and tablets. But data centers, they hadn't done all the same things in terms of sleeping the various components when necessary. But they've done a lot better, and they've reduced the overheads of the air conditioning and a whole bunch of other things. But there's still, we still have increasing demand for electricity from data centers. So what kind of percentage of the electricity of the world? Well, in developed regions, we're looking at somewhere between 2 and 4% of electricity being used for the internet and the cloud. That's crazy and going up. And as we know, it's not getting any better as we have more problems that we're trying to solve with data science and more data coming on stream from many sources, whether it's smart homes and cities or it's big data from health and environment and so on. So that's probably not a good thing. That cost is going to hit a ceiling at some point, and people will have to think hard about maybe thinking about energy efficiency in a different way there. Standards are interesting. Standards may be out there for safety and legal reasons or ethical reasons, all the above. So we do care about standards. In particular, of course, if you're doing open science, which most of the Turing work is pretty open, we might want to share data with people, and we might want to use formats that everyone's agreed. If you're working on healthcare data, the NHS in Scotland and Wales has federated their databases, and they have a set of schemas that you can go look at so you can figure out how, so they have a standard set of metadata to describe things, and that matters. And obviously, standards for software systems are helpful because then you can work to standard APIs and your code will port. It will work on a new system, hopefully, or with minimal pain. So this matters. But there are other kinds of standards you need to meet, which could be legal and regulatory. So there are obviously confidentiality, privacy, a whole list of standards there, which we could have an entire talks about. Anyway, so life is complicated. There are things that are not fixed. They keep changing. The law changes. Technology shifts under our feet. The relative costs of things change. The relative cost of communication compared with computing is, has shifted. And just to give a kind of feel about this, we've speeded up components roughly the same. The capacity and throughput of components has gone up at roughly the same, let's say, doubling every 18 months. So your storage devices every 18 months for the last 30 years. Your CPU speed has gone up every 18 months for the last 30 years. The internet got faster, literally, 1,000 times faster every 10 years, roughly doubling every 1 to 2 years. So all those three, communication, memory, storage, and processing, have all, but a very small difference in the ratio of those curves, right? A very small difference means one becomes more important than the other. A small shift in the relative performance of networking or the cost, literally monetary cost of networking versus processing versus storage, could change things. To illustrate that, an extreme point, the director of British Telecom Research 25 years ago, Peter Cochrane, a very smart guy, he proposed at some point in the future we could have storage devices that might be very slow to write but would have huge capacity, and that we might have enough capacity on a storage device that we put everything in the British Library on one device, and you give it to everyone, and you send it. Once a year you send a thing in the post to every person on the planet, and it has maybe 100 petabytes. That was quite prescient. There are people working in DNA-based storage right now in Boston and Cambridge, England, who have working devices. They're very slow to write, but they have that capacity. They're not practical yet. Once they're practical, then everyone would have a copy of the British Library. It would be peanuts to give every single person on the planet that, not just Wikipedia, just everything. All movies, all music. And the only thing they need to do, perhaps, would be to pay for a key to decrypt something that you were supposed to pay to see, which would take very little bandwidth. And suddenly you've just said, well, where's the business for people having high bandwidth networks? What are they there for? Well, they're probably there for humans and robots to talk to each other. But they're not there for downloading stuff anymore. That would be really inefficient. So you could imagine that world, which this guy predicted 25 years ago, might happen. It might not be practical. But those sort of relative changes, can shift your entire design, okay? And if you were a data scientist, of course, that could be, again, with encryption, you could imagine getting all of the UK healthcare data once a year you get that full set of data, and you run your machine learning over it in some secure fashion so you don't invade people's privacy, and you come out with a better model of some part of the healthcare system. Okay, so what are the resources we're playing with? This is very generic. We'll get onto detail later. Please read email if this is known stuff to you. So we're playing with time, space, computation, money, and labor. So let's go through some of these. Time shows up in task completion time, how long does it take to execute some process. Time to market, people forget about this. If you're working on some new thing and somebody's waiting for you to finish it, they might go to somebody else if you don't finish it in time. If you do it too early, you can come up with a really cool idea for some cool AI thing, and then everyone's like not ready for you yet. Self-driving cars probably a good example at the moment. Of something that's a bit early. I wouldn't put my money on those being a regular part of the landscape for a while. The people who are investing in those have big, deep pockets because they have other businesses they run, so they're okay. Mean time between failure is important. Availability is a really important number. So you might think a data center is very reliable. You might think your home network is not very reliable. Actually, if you're using your home systems to access your data in a data center, then the combination is the thing that matters. The mean downtime for a house in the UK is one of the best broadband access in the world. It's pretty good. We have at least 4 providers and 98% of the geography. But the average over all houses is about 2 hours downtime a year, sort of 1 outage. That's fairly bad, actually. And that means you can't get at your data. If you had your data locally, you could, of course. So it would be 100% available if it was copied locally. So if you cache all your own data, or you keep all your own data and only back it up in the cloud, that would be fine. So we've got metrics like response time, the time to complete a task, the throughput, the number of tasks per unit time. And then, of course, then you get into why parallelism. Well, if you just take this example, you've got 20 tasks to complete in 10 seconds. Each task takes 3 seconds, so it's going to take 60 seconds. The only way you're going to meet a deadline of 10 seconds is to do 6-fold parallelism there. And this could be, sorting office for post office. You need to hire 6 people to sort things, or it could be 6 processors, 6 cores, or 6 threads on a hyper-threaded architecture, provided you're not bus and memory limited in some other places, the bottleneck. So space shows up as memory capacity. We're going to see this big time in the second part of the talk with Spark. Spark and Hadoop have fairly large memory footprints, but also capacity and links. I should have said under time, of course, we have all these things changing. We have space time. These things are shifting. We have faster processors. We have more cores, more parallelism. We have more memory. We have more disk storage. We have more solid-state storage of various kinds, and we have high capacity links. The speed of light doesn't change. So despite a famous Italian experiment where they measured slightly better speed of light, turned out to be a measurement error. Some people were clocking stuff off of CERN in northern Italy, and they were saying, we're observing neutrinos that could only have got here slightly faster than the speed of light. Turned out, they said, this can't be right, and it turned out there was a measurement system error. It was like a really subtle problem. But anyway, we'll start with actually slightly below the speed of light. In most fiber, it's about 2/3 the speed of light, and you can't do much about that, right? And unless you're really crazy. I have a friend at Microsoft who said, when you go from London to Sydney, Australia, you go around the planet. Couldn't we go through the planet? Because you're basically pi better, right? So, and he actually proposed seriously building a neutrino signaling system. Where neutrinos go through the planet, but they do interfere a little bit with matter. But his proposal, this is not completely crazy, right? This is illustration of system thinking. It's a thought experiment. It's not practical. But imagine you're an ultra-fast trader, and you're in Sydney. You want to trade in New York. You want the edge. So if you could use neutrinos, you wouldn't send long, complicated messages. You might just send a 1 bit that said buy and sell, and it will get there faster than all the other competitors who are going around the planet. So you don't need a high bandwidth link, you just get this low latency. You see the trade-off there. And people in super fast networking companies, there's an outfit in Cambridge who build these ultra low latency Ethernet, 10 gig Ethernet Solarflare, build these really low latency Ethernet cards. People in the US build data centers for traders halfway between Chicago and New York, so they've got half the latency. Because there's nothing else you can do about the speed of light, right, without tricks like that. And these people have very, very deep pockets to pay for that stuff. It's annoying they can't spend the money on something like, better healthcare modeling, but never mind. Maybe they're making the money, then gets invested in healthcare somewhere else. Okay. And then, computation is the amount of processing can be done in a unit time. So you can use more processors. I actually made a joke about the speed of processors. We had a project in Cambridge working with the data grid, who were the people processing data from the Large Hadron Collider in CERN. And it was a huge amount of data that was coming across the fibers from CERN, going to all these clusters, big clusters of 18 clusters of, I think, 23,000 processors at some point. Anyway, it's a while back. And they said, we can't deal with this huge amount of data. It's, I can't remember, let's say it was 300 megabits a second. And this was quite fast. And we don't have enough processing. And I was like, well, if you wait 2 years, all the new Intel processors will be fast enough. Just turn off the Large Hadron Collider for 2 years and then wait, and stuff will be faster. And it wasn't a complete joke. It turned out they had teething problems anyway. And by the time they actually got around to doing things, they had faster processors. Or you might get the same processors for less money, so you get more of them. So money matters. What will people pay for a service? What do we pay? We're somewhat spoiled in the research environment. In the Turing, for example, we have relationships with Microsoft. They've very generously given us a lot of Azure resources. And that's, partnership. In general, if you had to go pay for that, that would be, significant money. It's a cost. And it got more expensive as a result of recent security problems. So their system got slower. So you're using, more of it to do things if you worry about confidentiality, which most of us may do. Depends what data we have. Not everyone. There's probably climate data is probably something you're not too worried about. You probably want people to check your data. But that's a different world. But healthcare, financial data, you probably really care about confidentiality. Labor matters, and this is a practical example from the UK again. These are all real-world examples. For a long time, we had quite good broadband in the UK. We had your fixed broadband. You'd have a DSL line on your old copper phone line, and you might get 5, 10, 15, 20 megabits a second download speeds. It was okay. And everyone was going, why don't we have fiber? And the French install fiber in some cities with government subsidies. And the UK is deregulated. We have competitive. So they were like, well, we can't afford it. And then there was this recession, and labor costs fell because there were people in the building industry not building houses. So it was cheaper to dig up the road. That was the dominating cost of putting fiber, was digging up the road to pull the fiber through new conduits. Once you've done it, you can reuse them to pull more fiber. And so then we're up to, I think, at least 10 million homes now with fiber to the home. And that's a big step forward. It uses less energy. It's way faster. It's lower latency. We can't beat the speed of light, but it's still better than copper somewhat. As you go to faster clock speed, the packet time to get on the wire is less, and so on. So that was kind of an interesting, cutover. And actually, when that happened, there's a second effect, which is once you've hired a sort of team of people, you kind of keep them and you dig up more stuff. You actually, use that fact because you're amortizing the cost of having hired them over digging up more roads. So you basically put fiber to everywhere you can. You go past a bunch of houses and you run fiber to the front of all the houses if you can. An earlier version of that was cable TV that got rolled out in some places, more in the US than here. Okay, there's constraints I've already mentioned. There can be sort of social constraints. Design might be, have to meet some requirement that humans like. You can have underspecified standards, which are a real pain in the neck, where people can argue about it. And market requirements which make life complicated. Compatibility with particular systems is a real hassle. If you're into the mobile sensing world, for example, some people in the Turing are working on using smartphones to sense well-being data, mobility, location, so on. If you want to have good non-biased coverage, you have at least 2 and probably 3 platforms you have to target with your software. You have to, you're going to have to do iOS for the iPhone. You're going to have to do Android, and you may want to do Windows Mobile because there are segments of the market in business and other places. And that will get you some reasonable fraction of people, because you should always remember that will be biased against people who don't have smartphones. So if you're sampling something from there, that's a separate discussion again. But then these are other constraints that put extra effort on any project. So scaling is kind of hard to. It is a constraint in some senses. It's not an obvious resource constraint. It can be hard to measure, but it's necessary if you're trying to do a lot of what we do. As I've said, data science is not always, but often has big data. big data, i.e. too much to run on one laptop. You can try out some subset, you can practice things, you can debug your software on a subset, on a smaller device. There's another value of debugging on a small device, which is also it gives you a baseline. So when you take your single task, single process, single thread, or whatever system, or single core system, and you put it in the data center and you run it on multiple cores, and you don't see a speed up, then maybe the other constraints in the data center were so bad that actually you're better off just getting a single system with more memory or faster processor, that maybe latency to do distributed computation is not, is the big killer. That can be the case. There are some classes of problem where you won't get a speed up. There's a very cool paper a couple of years back by one of the guys who worked on differential privacy, Frank Micheri, who was working on graph processing, and he noticed a bunch of papers that were taking graph data, so network graph, like the web, and doing various algorithms like k-click or modularity or some other thing, centrality. There are a bunch of algorithms you run on graphs routinely to get some property that tells you something about percolation time or epidemics, flood time, or whatever. And he noticed that a bunch of these papers had a new graph algorithm or new implementation of graph systems in a data center, and they're all using the same 128 core sort of benchmark to say, mine's faster than yours. And nobody went back and said, well, what happens when you combine all the speed ups? So they were all kind of speed up this way, maybe they were all orthogonal and all of them would add, but also much worse, nobody went back and checked their algorithm on one core. And it turned out that actually he could beat all of them on his laptop. So nobody baselined something, and that's a scalability question. That if the constraint is in a distributed version of the algorithm, you're going to be hit at each step of the iteration by a remote procedure call or a message time or whatever, then you may be barking up the wrong tree there. Not always, but sometimes. And there are lots of cases that comes up time and again. You see somebody trying to do a speed up. Actually, an example of this is very specific. Sorry, if you're into training a neural net and you distribute the training over multiple processes in a data center, and then you're running some kind of stochastic gradient descent on the output of each step of the training, and then you exchange the vectors of weights, you send them to all the other nodes running the training, so they can update their weights in their neural net and then move to the next iteration. If you have n nodes running this parallel computation of training, your classifiers over lots of data, then a naive implementation will have n squared messages, because each node will have to send every other node what it's learned in this step. Right? So you've taken this image, you've detected a cat, there was a cat. You detected no cat, there wasn't a cat. You update your weights, you send it to everyone else saying, okay, here's some more data to roll into your training. N squared is not a good idea for neural nets. So n squared exchange of messages with 10,000 nodes in a data center, you're going to spend hundreds of times longer exchanging all those updates than doing each step of the computation. You'll get no speed up. So then people do a lot of work in clever optimization in there, like they'll randomly select some of the nodes to send the update to, or they'll arrange the nodes in some structure like a ring and send it around a set of nodes, or they'll even drop the updates to some people because it's stochastic gradient descent. It will still do it. It will take longer, but if each iteration is faster, you're better off. So scaling is interesting. And the scale out, you sometimes hear marketing people talk about the cloud, they talk about scale out. They are basically saying that deploying the hardware and the software infrastructures for the cloud has sublinear costs. That means twice as many processes, less than twice as much money. That's because you get amortizing of the costs of maintenance, power supplies, air conditioning, all those things that are, that up to a certain limit anyway. And so putting more processes, more storage into a data center scales nicely. There are other systems that self-scale. One example is peer-to-peer systems that can work very, very well. So you just add more peers, you get more capacity in the system. The most famous probably example of a peer-to-peer system is the internet. The internet is not one network provider building a global network. It's just people plug in more stuff to the internet. Many homes now don't just have a router and a computer. They have maybe a little network in the home with multiple devices. They're part of the internet. The network is extended. Some people extend the service to their neighbors. You have community mesh networks to access the internet. In Spain, there's one that has 50,000 nodes, and people are up to 10 hops from the internet, are just going across neighbor. And that scales really, really well in cost benefit. So that's kind of another interesting factor. Okay, so we've got this issue of design where we find a bottleneck that may be a constraint on the system, and you want to figure out what we do about the bottleneck. So typically, you'd like to increase resources at the bottleneck, but you need to know how many resources you add to the bottleneck. So arbitrarily speeding up the bottleneck there's a diminishing return. If the network speed is the bottleneck for your computation, adding network speed will be good up to a point, and at some point you go beyond that, and now the CPU is a bottleneck, or the memory is a bottleneck, or the disk is a bottleneck. Okay, so there's a balanced system basically says all the resources should be just on the bottleneck. You can build systems, by the way, that are fully adaptive in the software side. For example, Microsoft had a really cool project in when they build you a service in the cloud, they use multiple copies of components. Let's see a simple example. Imagine you're offering a ticketing service for theatres and venues in London. A ticketing service will have a web front end for people to sign on and just see what's on and then go to a page and then say, I'm buying tickets to that. It will have probably a SQL Server backend to talk to a database which has been updated separately of what's on, and it will have some transaction processing system for payments. So you could have one of each of these little services for each customer. One person arrives at the web service, you launch them, their own little web server, their own little SQL Server, and their own little transaction processing box. Or it might be that one of those components is not the bottleneck. So maybe you want more of the others. And so Microsoft have an adaptive feedback system. They just use control loops to decide how many of each of these they need, and they measure the performance and increase or decrease the number they need appropriately. They use a bunch of cool control theory to figure out what the numbers are. And other people have systems like that. So when you compose services out of lots of little pieces, then that's a nice trick. You can't really do that with the hardware and that sort of time scale. In the hardware, you measure the system, and you go, okay, over the next year, we will provision more network capacity, or we'll put in more disks or more processors, or less. We're wasting money on some of them. Might be wasting electricity on some of them. So it's very, very hard to get everything perfect and a perfectly balanced system, that everything's right. That example down the bottom, I don't know if anyone's ever been to the original Ford production line in Detroit. Where they built the Model T as the first mass-produced car. It's the most incredible place, and it's still there as a kind of giant museum. So they had everything under control. This is like Ford was, the original control freak. So there's literally a canal where boats arrive with iron ore and rubber from the rubber plantations. And at the far end of this huge site, out comes a car with tires made of rubber and metal sheeting turned into the bodywork of the car, and an engine and everything driving off. And they controlled the dimension of every part of that system. It was optimized, so there was no bottleneck. If there was a bottleneck, they wouldn't be making enough cars, so their costs would go up per car, and they were trying to optimize the cost of cars. There's a political, interesting social story, of course, that I think this is anecdotal. I've certainly seen it disputed. But at some point, Ford realized that his workforce couldn't afford to buy the Model T car. So allegedly, he increased their pay so they could become customers as well as workers in the factory. And I've certainly read that a couple of times, which is a sort of another piece of the picture. It's slightly weird if you think about it. So you increase the cost of production of the car for the mean cost, but increase the number of people who might buy, and you have to think about timescales about whether that makes sense or not. I think it would depend on your sort of salary trajectory and the lifespan of the car and a bunch of other things. But anyway, that was very smart thinking. Another example, if you want to see a piece of history of very well-designed system, the entire pipeline of components being optimized was the Lions computer. There's a lovely book about it, a computer called Leo. There was a chain of restaurants called Lions across the UK, which had, there were restaurants and tea shops and whatever. And in 1950, there were two operations research statisticians who ran the business internally, and they decided they'd see if they could use a computer to run all the ordering, printing invoices, printing the menus, figuring out the salaries, printing out payroll, all of that. And so they built this computer. They literally went and talked to Maurice Wilks in Cambridge and von Neumann in Princeton, and he came back and designed from scratch the entire system, including how many printers they needed, of what kind for all these different jobs, what the task load of the computer would be, how often would it have to run the payroll, and so on. And they designed the entire system so they didn't have, there was no spare thing and there was no wasted thing. And it became a company called ICL, which became part of Fujitsu, which was a big success for quite a long time. For about 20 years, they were quite a successful computing company. And it came out of a corner shop restaurant chain. But because these two, the operations research, the original statisticians who really had methodological soundness, they figured out all the different components, the costs, and so on. And they got it to work, which is quite remarkable. Before IBM, I think, had a mainframe, as far as I know. So how do we use unconstrained resources to relieve a bottleneck? There are lots of different techniques for this. These are sort of standard techniques in lots of parts of the world we're sort of used to now. Early on in computing, you got a computer and it was dedicated to you. You literally walk up with a paper tape and you'd use the computer and get some kind of output which might be more paper tape, and you might have some widget to read the paper tape and produce some numbers. But nowadays what we do is we share resources, we multiplex resources. So your time-sharing systems, multiplexed data centers work because they're used by multiple users simultaneously. Even your laptop is being used, as you type. It's probably being used, your phone is probably being used by other users. People are sending you targeted ads, unless you're blocking them. Or even if you're blocking them, it's too late. They've already got to your phone. Or they may be sending you more useful stuff like software updates while you're sitting there typing. And provided there's enough resource, that wasn't a bottleneck, that's good, right? And good things happen. Or you run your task in background while you edit your paper about things, and up pops a graph with the latest results, and you go and update the paper. You can do these things in parallel. So multiplexing is a standard thing. Multiplexing is the basis of packet switching for the internet. The internet is a tool which does communication for simultaneous people simultaneously par excellence. That was the basis invented by a guy called Davis in a post office in England. Again, about 70 years ago, he came up with this idea. You don't have to give a dedicated link to people like the telephone net. We could send a packet from this person to that person, and send a packet from that person to that person, and switch them, and you get this shared resource. And it all works because you know something about the demand, which we'll get onto. So it's very important. You need to know something about how you schedule the access to the resource, because when somebody wants to use the CPU and then somebody else wants to use the CPU, you need to have some notion of how urgent each demand is. If you're typing a key on a keyboard, you probably need to respond real fast, because humans are pretty impatient. Actually, modern computer can probably do a few million instructions between you typing one key and another. So having responded to that person, you go off and do a whole bunch of other things. So that schedule is quite important. Crucially, you need to know something about the statistics of the demand, not just the urgency of different demands. So the statistics are the basis of how you dimension a data center or an internet link, or even a design of a laptop. You need to know, what is that mix? What does it look like? What are the distribution of mean and variance, or make life more complicated, likely long-tail distribution of demands from all these different types of users. And then you can figure out what the capacity should be. So if you've got n identical tasks, each requires capacity C. If NC is less than the specific capacity for each task times the number of tasks is less than the overall demand, then the resource is fine, so you can multiplex it. If 10% of tasks are active, then we can get away with 10% of the resource total and still meet the demands. Okay? So we need to know those basic statistics, but we also need to know about the variance, because you could get unlucky. It could be that people all arrive with their demand at the same time. So here's an example when you look at roads in London. The mean demand for roads in London is very, very little. It's like close to zero, right? Because between, let's say, 9 or 10 at night and 7 in the morning, there's literally no traffic. In fact, they should just turn all the traffic lights off just to save power. Some cities do that. But of course, the peak, walk out there on Euston Road, the peak is wall-to-wall cars. Congestion charge is an interesting mechanism, which is to push the demand back And this is a general idea of reducing demand by pricing and looking at people's price sensitivity to the point when the peak demand is just about usable. When that was done, it was quite interesting. When they first introduced congestion charge in London, the peak demand fell, and the mean went up to the point where the average speed of cars in London was like 28 miles an hour. Obviously, some people's speed. Where before that charge, the operating point was so bad that the mean over 24 hours was below horse-drawn carriages in Victorian times. And so you're getting a very badly multiplexed resource. Okay. You compare that, that's statistically multiplexed. If you compare that with the trains aren't statistically multiplexed. They're scheduled specifically on allegedly a hard schedule and a fixed timetable. Actually, the people getting on the train are a statistical multiplex. Okay, so you can have spatial or temporal statistical multiplexing. So you can distribute things over space, you can distribute things over time. And so the idea here is you can have, if only a fraction of tasks are active simultaneously, then if statistically you know that to be the case, then you can allocate the resource to the next person, first come, first serve, or maybe some other schedule, or maybe slightly different schedule, maybe some priority schedule, and then the next people will come along a bit later. And you can have, each task might be only active part of the time. So the classic example here, again, this is old school, but it's just to illustrate something. A simple example, if you're building a hotel with a telephone system, I don't think any hotel would put a telephone system in anymore because everyone's going to use their own mobile phone and internet. But imagine you were, you got a 100-room hotel, you could put in 100 phone lines. That would be silly because half the people in the hotel are not using the phone half the time, or most people aren't using. Maybe you only need as many lines as slightly more than the mean number of calls. And then somebody will pick up the phone, it'll be busy, and they'll try a minute later. But also, voice call is a statistic. When you measure speech, it may sound like I've been droning on continuously, but if you record the signal, as we're doing back there, you'll find about 40–50% of it is silence. And you can compress that out. And so most of the digital telephone systems in the world co-voice with compressing out that part of the signal. And so then you get twice as much capacity out of the system as well. So you may, instead of having 100 lines, you go down to 10, and they go, well, I get away with 5 lines worth of capacity out of the hotel. So I'll pay the phone company only for that. Actually, it's not quite that simple because they'll bill for call time and other random magic things they'll make up. So the point here is that to do statistical multiplexing and get the reuse of your resources, you need to know the statistics, right? So if you're building a set of tasks over a data center and you're sharing that data center with other people, anyone here working with healthcare data, running stuff in Edinburgh or on the data center there, you need to worry about there are other people running there. And they need to, people running that data center need to worry about it. You need to know about the statistics of demand. When they federate data, they pull data from multiple places. There's network demand. When people run a large multi-processor task across the data center, there's CPU demand. There may be storage demand. I don't think that's one of the examples where they have that as their limit. Pipelining is another important thing. You can set up a line of work as a sequence of subtasks. You break it into independent subtasks and then execute them in parallel, but you have to start them as that sequence, so you have to fill the pipeline. A classic example of pipeline everyone sees, if you go to a website, websites have multiple objects embedded across a website. Actually, they're way more complicated nowadays. There's not just text and images, maybe even JavaScript code arriving. There's also stuff arriving from other places like targeted ads and so on. So you can pipeline the processing of the web page components arriving in the browser by rendering them in parallel with network fetching. So that's clearly a good thing to do because the user experience is improved because the latency before you get the web page goes down, right, by doing that. And clearly, doing networking in parallel with rendering on a screen is absolutely trivial. It's not a big problem. Nowadays, even the most simple device has, even a low-end smartphone has a core dedicated to talking to the radio to do networking and a different core dedicated to running Android or iOS to talk to the screen and run the apps. Actually, it gets better. Most phones have 4 cores and they have one dedicated signal processing for doing clever stuff, and one to do speed ups of graphics. You might even have some little GPU on there doing some work. So it's pretty sophisticated. So, but of course there are dependencies between subtasks. So you have a sort of wait for graph. This one can't start until it's got output from the previous step. So this is just illustrating serially dependent subtasks, and you fill up this assembly line. This goes back to the Ford example, the production line of the car. You pull the iron ore and rubber off there, and the rubber goes over here in parallel with the iron ore going over to smelt to go to make sheet metal, whatever. And then rubber goes down to some place where they get the wheels and they put the tire on the wheel, and so on and so on. So you can fill up the pipeline. There's a latency to having pipelining to fill up the pipeline, but once it's going, you get more throughput. You get the parallelism of the pipeline. Okay. This, if you were at the previous talk by Mark Handley on Spectre, this is not speculation yet. This is just pipelining. Speculation is when you go further and you say, well, we're not sure if we're going to do these tasks in the pipeline, but we've got enough resources to do them too, so we'll do them just in case they turn out to be useful. Okay? So if there's a conditional branch in some piece of code, and you go, I could do this bunch of stuff, or I could do that bunch of stuff, you start doing this bunch of stuff and that bunch of stuff if you've got the resources. And then sometime later you go, oh, well, we finished this one, and then it turns out the if was true, so we'll stay with this and we'll throw all that away. And therein lies a whole problem. So there's a way of computing simply, the parallelism you get out of the pipeline, or how many stages you want to balance the pipeline. This is exactly the same as what we talked about previously when we were just looking at simple parallelism. We're just doing the same thing, it's just that you have to worry about dependencies in the tasks unless you're doing speculation, in which case up to the amount of resource you have, you might just fire that up. Just remembering speculation or pipelining has an energy cost. You run all these resources, and you might not need all of the steps in the pipeline, and the energy cost, is real. And so lower-end phones don't suffer from speculation attacks because they don't do speculation because they're trying to save energy. So this is a good thing for some people. Batching is another trick, and this is sort of a similar trick to pipelining, but it's where non-dependent tasks have some element of work that's the same, so you can amortize that bunch of work over a bunch of tasks. So you batch a bunch of tasks, like setting up a bunch of things for all of them, and then proceed with them. So of course, like pipelining, there's a delay, there's an extra latency to setting up batching. You have a bunch of few first steps, but once you've done them, now you get a multiplier of some kind, having amortized the overhead of all these tasks. So this is yet another kind of standard technique. These are applicable. I'm trying to illustrate the breadth of applicability of these, sort of way of thinking about systems. Locality is another really important technique. I already talked about lots of examples of this, but you can have spatial and temporal locality. So spatial locality is really simple. You've got a copy of data on your laptop. You don't have to wait for the time to go fetch it from a server. Okay? Or there's a copy of the book you want to read in your bookshelf. You don't have to go to the library or the bookshop and borrow it, or worse, order it on Amazon, and then it arrives, super fast, only a day later. So spatial locality is important, and you can exploit spatial locality in lots of ways. And one of the things we're looking at, there'll be a talk in a couple of weeks on this, is not using data centers at all, but leaving everyone's data on their laptops and then pushing the code to everyone's laptop to compute some interesting machine learning over a bunch of people's data. That has privacy advantages, but it also has potential latency advantage. You move the code may be much smaller than a large amount of data. Moving all the data to the center has other downside. And then temporal locality is just, something's about to happen soon. So we've already started doing X, and Y will follow soon, so we're going to get some benefit by waiting for that to happen and doing it at the same time. And all of this results in techniques like caching. Caching, where you download something and you finish using it, but keep it around because who knows, you might want to use it again. Okay? First example that people may have encountered was, you may not have noticed, but 20 years ago, Berners-Lee created the first web server, and the CERN HTTPD, first web server that people were using, did caching. So if you ran one on your site and browsers were configured to say do caching, and the server was configured to do caching, then the first person would fetch some important paper or piece of software. It will be stuck on the local server. The second person will get super fast latency because it was already there. And that has both spatial and temporal, because people are interested in the same thing at the same time in the same place, right? Somebody tells you, hey, there's a cool talk about X. If you go to this site, it's on YouTube. YouTube do global caching. They have copies of any popular video. As soon as one person in London looks at a video of a cat falling off a wall in Beijing, it's on a cache and a YouTube server in London. Actually, they have a threshold. So as soon as a few thousand people looked at it in the first place, now it's become popular enough, it's worth caching. First person looks at it, now it's copied everywhere, and all the subsequent people get local access. And that's because interest is localized in time for content, and then it's typically also common across regions. People are interested in the same thing because somebody nearby them told them, their social network told them, and most of their social network is nearby. Optimization, when you're optimizing something, this is a standard 80-20 rule. And again, sorry for those of you who live and breathe systems, but it's not worth optimizing all your system. Large amounts of your system don't get used a lot of the time. Only optimize the bit that's used a lot. And there are examples for how to optimize systems from different timescales. The design of processors, ARM started, I don't know, 35 years ago, was optimizing for the most common instructions used, and they created a much simpler processor, which is lower power budget than Intel processors, because it was just the common case. The PowerPC has a processor which has actually got an amazing instruction, which is a floating point multiply and add, I think even vectorized. And that was, people looked at that and go, that's insane. Why would you put that in a RISC processor? And it was because IBM were designing the processor, said, one of the common things people do on this is scientific programming. One of the really common things that people do is floating point, and they do multiply and add because they're doing vector operations. So they optimize for a common case, okay? And they counted that. They went off and looked at lots of programs, said that shows up in many programs. On the internet, the protocols the internet runs are optimized. There's a thing called header prediction that runs that says the most common packet we see is foo, so we'll code in most, certainly in Windows, OS X, Linux, that the code is written to deal with the common case first. So you only go through like 40 instructions to deal with a TCP/IP packet. If you try to do everything for the general case, it's 3,000 or 4,000 instructions. So this thing's way fast for the most common case. But there's a limit to how much you optimize a tool, and this is Amdahl's law. It's only worth speeding up to the point where there's diminishing return again. That's basically what he said. Funny, you get your name on laws that are kind of very general statements of common sense at some level. And that's good. Hierarchy, decomposing a system hierarchically is often a good way of breaking things down into subcomponents. There are lots of examples again. If you have a hierarchy, you may encourage locality spatially and temporally, so it may be a useful thing to do. You may increase reliability by not having a single point of control. It may be an advantage, may be a disadvantage. When you have a hierarchy, communication at the lower levels of the hierarchy may be better or worse. It depends how you design it. Data centers, a good example. Data centers have a hierarchy of switches, and there are these core switches which are super fast. There are top-of-rack switches. There's switches between, in the switch fabric between processors and system units, and there's a trade-off in the communication. So you're making assumptions about does most communication go up and down the hierarchy or between nodes at the bottom. That's kind of part of the design. Systems in the internet infrastructure, like domain name system, is again a hierarchy which gives you good caching capability, good locality in space and time, much like web caching does up to a point. Binding and indirection, another couple of techniques we have. So you can generalize a piece of code by saying, okay, well, we'll deal with this case by name, and then we'll map the name to the specific example later. And so that's indirection plus the binding happens at actual runtime rather than at load time or link time or build time. So these are sort of translation tricks that happen later. So there are many examples of late binding, it's called, but it basically sort of defers making a decision, but then means your code can be more generic. It has an overhead, but it has an upside in terms of scaling in some senses. And virtualization is one of my favorite things. Obviously, the internet is a virtual network. It's a network of networks. You don't care about the details. They're all hidden below the IP level. Below the routing of BGP and so on. Operating systems are virtual systems that hide the fact that you might have one CPU or 4 CPUs. You might be running, I don't know how many processors are running on here, but probably a few hundred typically in OS X and so on. There are lots of examples of virtualizing a resource, but basically it's combination of indirection plus multiplexing. So virtualization is not magic. We've covered the two basic techniques already. You multiplex the resource, and then by naming it in a way that has a little bit of hierarchy, you then have this hidden system below there. You don't care that there were only 4 CPUs and you had 400 processors, the mapping is hidden by the binding. Of course, if you're in a system performance area, you may care about something like core affinity, because maybe cores have local memory, if you're into that space, and you care about the resource being local, or you might have network affinity to a core and so on. So there are other things you have to care about. My favorite example of virtualization, and this is sorry to disappoint people who still believe in Santa Claus, but Santa Claus is a statistically multiplexed virtualized resource. I think it's a fair example for grown-ups. There are any kids in the room or out there. I hope they're not watching. Okay, so and one of my favorite things in computing is this is a trick which I already mentioned in the context of training a neural net in a distributed environment, which is if you do the naive training, you n nodes finish each iteration and then send each other the outputs and then recompute their weights and so on. Then you have this n squared messages. But you can randomize when you do that. The gradient descent stuff will still work. So randomization will deal with spreading out load from a peak, sudden peak, will spread it out. Okay. What's another example of randomization is when you have contention for resource, you can tie break by doing something randomly. One of my things I always want to try, I don't think anyone will let us, but I can't see what's the problem, is imagine you ask a sat-nav for a route somewhere, and there's 2 routes that are nearly the same. Imagine a lot of people are going there. They're going to, I don't know, the races in Newmarket, and they're all driving from London, and they could go up this route or this route. What you really want to do is to randomly allocate people to each route. You don't want to say, everyone, the first 10 people go here, and then that route gets really, really super busy. Okay, now the next 10 people, and that gets super busy, and then the next 10 people. What you'd like to do is spread people out. That random load balancing is used in data centers today. You route traffic between those in data centers because there are many possible routes there's a very high interconnected data center that is used. So randomization is your friend when used carefully. Okay, it's a cunning technique that's jolly good. Another technique we use in distributed systems called soft state, where soft state is where you instantiate some state that's required to speed things up, but you don't care if it goes away because of some other resource. You make sure that it's sort of a statistical improvement. And it's just here's something that might help. It's like a hint, if you like. So that's the basic sort of speed up idea there. And it will just go away after some time. It will clear itself up. It won't do any functional harm. It might do some performance harm if you get the timing wrong and so on. Okay, I'll skip that for now. And I will skip that because that's very network specific. Extensibility is an interesting thing. So if you're working in a large research project and you write some cool code, not only is it a good idea to actually document it and debug it and so on, it's also a good idea to think about how people might actually extend it. And so this is a very good reason to utterly condemn anyone who uses Perl for large projects. Because you'll go back a year later and have no idea what that code means. And I'll forgive you if you go for Python, but there are many examples. There are people here working with languages like Julia or Rust or Scala, which are all fine. But also, in your system design, think about extensibility. Think about what will happen if somebody else, if you've built some component that's really useful, it's generically useful, build it in a way that somebody else might go, well, I want to add this other widget there. Back in the day, some of you may remember, there were numerical algorithm libraries for Fortran programmers in the 60s and 70s. A thing called NAG was a really good, studied in Oxford. And and this stuff was seriously good code. And it was built in a way that was maintainable and extensible. People could write, really heavy lifting. And so that's, and rightfully got a lot of kudos for building systems that lived a very long time, decades and decades. It's really, really cool. And of course, you could be a Linux guru and be going, oh yeah, Linux is like that too, it's extensible. It's infinitely extensible, unfortunately, arbitrarily into messy worlds. Okay, so sort of the bottom line is, if you're doing system design, you may want to do something quick and dirty, that's fine, but you should still bear in mind a bunch of these optimization techniques or these sort of performance improvement techniques. But if you're doing them, don't throw the kitchen sink at everything. You want to measure the system, figure out where the issues are, what are the bottlenecks, where would you gain from parallelism pipelining and so on, for all those different techniques, where would you gain from virtualizing some of the resources? Do you have statistics to do statistical multiplexing, or is it actually something you're going to use all the resources all the time, so you don't care about that? It's just a full-on system. So there's a sort of design cycle for systems that it's kind of common sense, I think. Okay, so just acknowledging Keshav for these slides. So that's the end of this bit. So I'm going to propose a 5-minute bio break, if that's okay, and then we'll start on the second bit. The second part of this talk is sort of quite a different area. And this is kind of reporting on a project that we have. So this is ongoing work at the Turing and a partnership with Imperial College, which is large-scale distributed data and systems group. Peter Pitzuk was a PhD student in Cambridge a while back, and he's now professor at Imperial. He does great stuff. It's really, really cool. So this is a project funded at the Turing from the defense partners, but we have an interest in healthcare and financial data, and you'll see why in a bit. And the topic is sort of Java runtime integration with Intel SGX Enclave. So we'll get onto all the pieces mean in a second. So basically, I'm going to talk. This is I should credit this piece of slides. So straight from him. So we're going to talk about why do you want an enclave for doing things? Why does this matter? How does the Intel software guard extensions enclave work? How we have enabled that to support arbitrary binary applications from the Linux world. And then what we're currently doing, which is to put the SparkR system for data processing, which is basically MapReduce plus RDDs. And I hope some people here are reasonably familiar with that, because I'm not going to dive into the details of resilient distributed data. It's a very cool thing that came out of Berkeley is in the Apache Spark system. But how we're squeezing that into this enclave environment. And then if you're interested in any of this, we're putting the code out there. It's very alpha, so if your main task is in trying to get something to work in Spark, don't use this unless you have a hobby interest and you're super, that would be great if anyone's got any use cases, which we're always on the lookout for. So why do you care about trustworthy data processing? So it's a question of the threat model. It's a question of who do you think is the problem? And so in a traditional data center cloud environment, you upload your code and data to the cloud, and they run it for you in some virtual machine, and they have a whole stack of stuff, including hypervisors and guest operating systems and blah, blah, blah on the cloud platform, and they have all their own people. And the assumption in the current classic cloud is that sort of everyone trusts those people. And to be completely fair, evidence is that the big cloud providers are pretty trustworthy. They're very good security processes. There have been very few breaches from a cloud provider that, somebody like Azure or Microsoft Azure, AWS, Google Cloud, all these providers, they do a pretty good job. There have been breaches from applications from people's own code or their own storage, or people uploading to cloud storage without encryption, but not because the cloud provider did something wrong. However, you may care about this. So the problem is the traditional principle of least privilege in security. So this is now, we've gone away from systems overall design, we're now sort of deep dive into particular security. The way we build systems is that the lower level you go, the higher your privilege. So sort of the hypervisor and the hardware can look at anything, then your guest OS can look at all the code memory in its address space, but not on others in principle. An application processor can look at a memory of the application process, but not of other processes. So you have that hierarchy, and that's been around for 40 years or more, and it works fairly well. In a cloud environment, you have multiple tenants running in a cloud, and you have high-value things going on, and so there are bad guys out there, and there are bits of bad code out there, which lead to possible attacks on this environment. And the problem is that the lower level the attacker uses to enter the system, the lower level they exploit a vulnerability, the more they can look at. And so in your what's called a multi-tenant data center, you're running on one of these big cloud providers, there could be tens of thousands of other customers. Some of them may be good, some of them may be bad. Some of them may be just watching out for vulnerabilities. When you look at the low-level hypervisors and operating systems, vulnerabilities show up, kind of once a week. And that basically means that every single process, every single guest operating system on a provider at that point is potentially visible to anyone who exploits that vulnerability. And if somebody's running a scanning attack to spot for that, they spot it, then they just read all your memory, they read all your storage, and they extract everything. Okay, so it's not that the cloud provider is untrustworthy, it's that we put all our eggs in one basket, and a vulnerability now becomes an attack on the entire basket. Of course, there could be agencies you don't trust. So post-Snowden, we're not sure in Europe that we trust the American government to not exploit backdoors to cloud, officially or unofficially. So that might be an issue. And we have legal constraints over whether we can put data outside of an area anyway. But so we have to do our best. Okay, so if you want to flip the model, if you're the user, you'd like your code to be secured, you'd like your data to be secured at all points. So in transit, when it's networked, in storage, on the cloud or in your home system, and during processing. Because when you process data, you pull it off disk, it may have been encrypted, now you decrypt it to run code over it, and then it's readable in memory, and so something that exploits a vulnerability in your OS code or in the hypervisor, then you're putting yourself at risk. And if it's, like I say, confidential data, it's surveillance data for intelligence, or it's healthcare data, it's personal records, or it's financial data, you actually have a legal obligation to not break, you have to meet some reasonable level of best practice at minimum. I am not a lawyer, but I work with some lawyers, and they'll beat me up if I said it like that. But I think that's sort of basic principle. You should do your best. So certain minimum. Okay, so along comes trusted execution environments. So trusted execution environments flip this model, and they say we'll have hardware support for running trusted execution, which is not accessible by hypervisors or the operating system through vulnerabilities. It is basically extra hardware support to run in a different. Think of this as a processor mode. It's my favorite way of thinking about it. People don't talk about it that way, but when you flip different levels in classical systems, the hardware supports processor modes for kernel device driver access and for user space. And now we have another one, which is a trusted execution environment. And Intel provided SGX, which is the software guard extension, is one way of doing it. ARM have a similar thing called Trust Zone, which is somewhat more constrained, but has been around longer and seems to be pretty robust, which is good. So this basically means that unprivileged code is not accessible by allegedly privileged operating systems anymore. Unprivileged data is not accessible. And it has a number of other properties like attestation, which we'll get onto in a second, and it's available. So this is kind of a good thing. So Skylake processors have it. So what does this basically do? So trusted execution environment is a sort of generic term for this, and we talk about enclaves. We execute code in an enclave. We'll see how we get into the enclave, but it provides controlled entry points to start code in the enclave, to finish to exit the enclave, to move data in and out of the enclave. You have to be very careful there. But also, importantly, it provides confidentiality through encryption of memory. Ta-da. This is a step forward. Not just disks where you can run software to encrypt things or decrypt, but the memory has hardware support for encryption and decryption. And the keys are owned by the processor, not by some magic somewhere where they can easily be stolen. So that's important, that architecture. And also integrity checks, so that your code can't run if it's been modified since you put it in the enclave by some bad thing. And you also get mutual attestation that this is the enclave, not some random person. You get local and remote attestation, so you get the attestation that says, I am running in the enclave, I'm not running in some virtual environment. Think of some science fiction story where we're all living in a simulation, right? And you can get remote attestation that says, yeah, that is an Intel enclave that's doing the right thing for you. And it supports threading. That's actually one of the big differences between Intel style of enclave in SGX and ARM. And I don't know enough details, but AMD have a slightly reduced capability for doing things, but have pretty good enclave support as well. There are other processors in the world. RISC-V is an open hardware processor from Berkeley and other people, and they're working on enclave support, and we have some stuff in Cambridge too. So a lot of people think this is, it's not going to be panacea to fix confidentiality, but it reduces some of the attacks. It reduces, the attack surface is reduced, so it makes it harder for the bad guys. Or the accidental shoot yourself in the foot experience. Okay, so you have normal user space stuff happening, operating system, application code, and now you have an enclave, so you have some block of memory where you can put code and data, and then the processor can go into a mode where it executes the code from that block of memory and on that data in that block of memory. So that's the basic gist of it, and there's a whole bunch of support for this, including threads in there, which can run application code sort of in some safer way. So this has been around 3 years on Skylake and other processors. Not all processors support this, obviously, you go back a while. So yeah, it protects confidentiality and integrity, so all jolly good. Basically, there's hardware and instruction set changes to the Intel processor. Same true in AMD and ARM and all the other processors. So that's why you need one of the newer processors to have this. And one of the things you get is a memory encryption engine. So there's something that sits on the memory controller that says when we're in enclave mode, we need to use a key to encrypt and decrypt things to and from memory so that we don't reveal things, okay? So that's a good thing because that means renegade code over here, reading across memory doesn't get anything. It gets grubble stuff, just encrypted stuff. You could not do this in any sensible way in just software. You could obfuscate your code. There are clever ways to obfuscate how memory is accessed, but there's performance overheads that are crazy. So having the hardware support for the encryption engine to do the memory access is fairly important. Maybe there's discussion about whether some other technique like fine-grained access control might also work. So other people have looked at that. Okay. So that's the basic notion, and then you have to get ways of how do you get in and out of this enclave, right? So it's sort of like this extra safe in the middle of the processor and the memory architecture and the processor. How do you get in and out? So there's ways to start executing code in the enclave, and there's ways to return output from it. And obviously, if you take something out of a safe and you hand it to somebody on the street, you've just blown your security. So you have to be concerned with how do you put things into the safe and get them out. So let's assume a world where people have done the other good housekeeping, that you encrypt things when you send them over the net. By default, most people move data around with HTTPS, which is pretty good. You encrypt things when you put them on disk. There are plenty of tools for doing that. There are file systems that support encryption. Now, you read your encrypted data into memory. You call some enclave start routine, and then you say, here's some encrypted stuff. Go away, decrypt it, do your processing, encrypt the results, and output them. That's the basic pattern. So we have this enclave page cache. Now, here's the fight that we're having. This is a nice fight, which is you only actually currently have 128 megabytes of encrypted memory supported, and of which you can only actually practically use 96 megabytes. Now, I come from a world where 64 kilobytes was enough for a whole operating system. So I don't find this alarming. But if you look at a platform like Hadoop or Spark, then this is quite a limit. Not very much memory. And if you're used to, notice it's megabytes, right? This isn't, 7-year-old laptop has got 8 gig of memory. So you're only allowed to get at this small fraction of that in this mode. So that's a bit of a challenge at the moment. Future versions from Intel will upgrade that, and AMD have a different approach, so we really need to go and look at the AMD stuff fast. There's another bug here, or limitation, sorry, that's not fair. It's not a bug, but when the memory encryption happens, decryption happens, you fetch, of course, from main memory, from RAM, into cache. But at that point, it's now in plane in the cache. So side channel attacks on the cache will work. So somebody's very clever who does an attack, which we heard about a couple of weeks back, and we showed that does work on SGX. You can attack the cache. It's quite hard to do those attacks, but what we've done is we've shut down one form of attack, but there's still another open, so that's kind of an issue. SGX supports multi-threading, so there's a thread control structure. There are some limits on what threads can do to stop sort of cross-thread contamination. I don't have time to go into details. I can give people a copy. The slides will be up on the net if you're interested in this. We have a lot of technical report on this as well, so it's coming out, so you'll be able to read a lot more detail. Okay, and then you can use more memory because SGX supports paging in the normal way, so you can page things out of the encrypted memory into normal RAM, okay? However, that involves encrypting in software as you go out to RAM, and so you take a massive performance hit. So it's way slower than normal paging. So you really want to avoid actively using more pages of memory than you can fit in the enclave at the moment. In long run, Intel will increase the number of pages. I don't think arbitrarily, but at the moment, this is kind of a no-no. Okay, so this is a very noddy example of just using the enclave. So here's some general untrusted code, which is going to cause something to enter. It's going to essentially enter the enclave, and then in the enclave, this code will execute, which is basically taking input, copying the message into an input buffer, verifying a MAC on it, and just checking it's got integrity, decrypt the message, process it, encrypt the answer, and then output the answer, and then exit the enclave. And now that code out there gets the answer, and so you've now basically, you've done an RPC between some code in normal memory and the enclave. You kept everything encrypted in normal memory in a normal processing mode. You've entered the enclave, run some stuff, get an answer, encrypt it, and output that to memory, right? So that's the sort of pattern of use. That all the work is in that bit in the middle. Process, what would that be? So what we're going to put in that process input is a bunch of Spark code. You could put anything in there. Microsoft have a project, very nice project called Confidential Cloud Computing, where they put SQL servers in there, and they put Hadoop in there, and some other stuff. Other people have put other things. But that's basically the pattern, okay? So you're getting hardware support for the things running over here, so that when they're doing things fetching from main memory and output to main memory, although it's being decrypted in that step there, it's still hardware encrypted, so somebody else reading memory can't see it. Once you fetch it into the cache, somebody can attack cache, could look at it. That's hard to do. And they'd have to know how to do that and where to do it and so on. Okay, so to construct the enclave, this is the sort of, where we had it earlier, we had EENTER, which is like, I'm now going to go into the enclave. You have to add code into the enclave. You have to take all that code you want to execute in the enclave. So basically, it's done by paging in the code. So that has an overhead. I just mentioned paging has an overhead. So you want the code to stay there and run a lot. So you want to do something like a MapReduce or Spark tile, run the stuff a long time. And you start your general application process, and you move some code to the enclave, and then it's sitting there could be doing stream processing, MapReduce processing, or any processing, and you've got some. Because the longer you leave it there, the more side channel attacks might be an issue. So that's a kind of interesting issue. But that's just basically illustrating this. What about the integrity of our code? Where's the check there? So this is just a, what happens if somebody tampers with the enclave code? So here's our original code that's supposed to be running securely in the enclave, and some evil person has put an extra line in here which copies a message. They've changed the code, right? That's all that's showing. They put an extra line, and this extra line is, if evil intent, it's copying the output of processing to an external buffer, unencrypted. It's just going, this could be, a bad guy trying to attack your enclave code. Can they do that? And the answer is no, they can't do that. You can't modify the code because the adding code to the enclave has integrity checking, okay? So basically, there's a sort of measurement process which just hashes the code as it's going page by page in, and if some page has been modified in some way compared with what you had out there in there, then you'll get an integrity failure, and the system will go, no, I'm not running that. We'll just go, no. Okay, and you can test that, and it definitely works. That's a very simple technique. Okay, attestation is this trick of, you need to know, is this an enclave I'm running on? It's not somebody simulating being an enclave, pretending to be. And then you also want to know, is this really an Intel enclave that's approved by Intel? So there are two steps to that. One is local attestation, which is sort of proving enclave's identity, and the other is remote attestation, which proves that this is Intel enclave to that other person. So if you're going to send output to that other person, they can go, oh, yes, okay, I now believe that. So imagine you're in a big distributed data center, and you're running on enclaves and running Spark across all these different nodes, and you're doing this MapReduce function over your RDDs. You do one of the RDDs, you output it encrypted, you send it over the net encrypted to one of the other nodes so it can go on with the next step, which could be training a neural net, whatever it happens to be. And that guy needs to know that you are one of these guys, and you're interloper or some other person. So that's why you need the remote attestation as well. So this is basically just classic crypto protocols for attestation. This is like, anyone use secure email here? I'm amazed. secure email where you want to know that the recipient is a recipient. You want non-repudiation of recipient and sender. Most people don't bother using this stuff, but it's routine. You can do PGP or whatever. Anyway, this is the same for processors. It's saying, yes, I am one of Intel's processors. And there's some secret stuff, secret source that Intel have, the CPU fuses and so on, that mean that this is not fakeable by somebody would have to be a very, very big state actor to fake this. They need a lot of resources to fake this. It's not something you can fake in software. You'd need to be able to build processors that look and smell and feel like Intel processors and fake out the key. It would be awesomely expensive. So it's sort of unlikely attack vector, except for maybe some very big foreign government, one day maybe, and they won't bother doing it yet because this has only just come on stream. Okay, so that's what all that set of steps are. And the remote attestation is just doing the same. So it's like I'll need to move along. Yeah, so limitations are current SGX. Memory limitations, quite severe for modern programmers. I don't know why modern programmers think they need so much memory, but there you go. People think, I forgot anything less than 4 gigs. It's a real problem. Well, here we're down at, tens of megs, so you have to worry. The middle bit of a lot of machine learning, by the way, the sort of core piece of code, is often quite small. The data may be bigger, but then, of course, if you're stream processing or you're doing MapReduce, the amount of code and data at any one time can be quite small. But there may be a whole bunch of other code around it, and we'll see in a second that we can exploit the fact that the other code doesn't need to be in the enclave. So this may not be a limit. Future versions of SGX on sort of the plans that Intel told us will reduce, we'll relax that. There'll be more memory available somehow. And then I mentioned the performance overheads are an issue. If you exceed the memory and you page out, this has a big hit, and side channels are a real possible attack vector, so that's an issue. Okay, so what the Imperial folks have done in this project and previous work is they want to support multiple applications in the enclave. So we contrast that with other people who've done some early work on SGX, where they put particular application in the enclave. So the goal here was to be more general. So the first way you be more general is you support a general purpose operating system. So the trick here is, well, you don't want a full operating system because operating systems work by having traps and other things. We only need the core bits of the operating system that support applications, and particular runtimes for applications, and then you get all the applications. So if you've got a JVM or .NET support, then you can support anything that runs on that, which would be anything written in Java or anything written on .NET and C# or whatever. It does require a lot of work. So one of the tricks is to use, rather than a full operating system, use a library version of the operating system, which is a stripped down version that runs as a library that's just linked with the application, dynamically linked with application code. So the Imperial sort of intercept here was to use a fairly standard, widely used Linux kernel library. There were other library operating systems they could have used. In Cambridge, we would use our own unikernel system, Mirage. But we're currently doing that on ARM Trust Zone rather. There's a comparison, there's a different way of doing things. There are other Linux kernel libraries out there. So this is just, it's just a practical thing. But the point about getting Linux kernel library working here is you basically get support for anything that runs on Linux. So if anyone's ported a JVM, for example, Oracle's open Java runtime, and it runs on Linux, then you've got it modulo the memory footprint of the whole system, right? So we're gonna modify LICL, as it's known, so that it can enter the enclave, and then anything it continues running after that, it dynamically loads, will be in the enclave too. Okay? Which is a tiny amount of code. It turns out there are all kinds of horrible extra bits you have to do, but it means you get a bunch of other pieces that you just get code to support block devices and other things. But you can't actually do device I/O from the enclave, so now you have to do intercepts for all the network and storage I/O to exit the enclave, or enter the enclave and encrypt, decrypt data, as my little example did. So we have to write a lot of pieces for that. So you take all those devices and you add in some stuff. Luckily, a lot of people have done work to do block storage and network encrypted and decrypted I/O. So that's sort of stuff lying around in libraries too. We don't have to make that up. And there's good reason for reusing that code because it's been tested and had a lot of people trying to hack it, and so it's probably quite good. Okay, so So you end up with this kind of picture also with dynamic loading. There's a hack to do with where you load in memory because SGX has some constraints about what you do there. So, and this is just the steps in loading the whole system. So once you've got libc running, then anything that sits in Linux or Unix world on libc, which is a POSIX compliant version of things, can load the application code, which could be a JVM, so you can run Java and Scala and therefore Spark. Okay. This is what I just said about how you do device I/O. You need to get to storage, you need to get to network, but you can't just call device drivers in the enclave. So you have to split top and bottom halves and then do some inter-process communication out of the enclave to do that, and you have to do that with encryption. So there's a way of doing this through device mapping with encryption. So there's a and then there's the network stack is a similar thing for getting in and out of networking, because clearly you're building this so you can support Spark apps or any apps that are running on multiple nodes, and they need to send interim results to other nodes to go on with the next step of a map reduce over a bunch of processes, right? So you have to have secure network out of the enclave to get to the other nodes. The other nodes also want the attestation, of course, which we've done before. Okay, and there's some even GDB support, so you could do debugging if you do low-level debugging with GDB. So that's just in there. Yeah, so we've got anything that works on Alpine Linux will just run now in that modulo memory footprint, which will hurt you, but it will work. It will just maybe go very, very slowly. So I'm going to skip that. So that was just, other people have done this too. There's a thing called Graphene SGX, which is a different port of how to support arbitrary binary applications on things. So this is not a mad thing to do, and people think it's maybe useful. Okay, so our next step was, okay, well, we can support arbitrary apps, but maybe we want to optimize a platform for data science. And we picked Spark. You might be a Flink user, or you might be using, I don't know, TensorFlow. And one of the things we're documenting in this work is what we have to do to make this work and work reasonably efficiently. And then people could then take one of those other platforms for data science and machine learning and port it the same way. And we hope that would, this has been, I don't know, 4 or 5 people at Imperial, and then one person Imperial, one person here for a few months. Actually, by next month, it will be a year's work. So it's a lot of hard work. But to redo it in another system would not be too crazy. So once you've got all the things written down, it's kind of, okay. So, yeah, so secure big data processing is a goal. This is Turing, so we do data science, and we want to have this way of potentially reducing the risks of the things I talked about. So could you do Spark over healthcare data in the cloud and not risk accidentally leaking all the data, or some bad guy just running in the same cloud center, scanning everything, finding one of the vulnerabilities and pulling everything out. And so, so this is just a typical little Spark example of, this is a canonical Spark example. It's like word count basically over a set of data. We have a bunch of others working, non-trivial ones working. So if this is just to illustrate what we're doing. Okay, so yeah, so the project is called Maru for historical complicated reasons I won't go into. And the idea is, can we get leverage? Anyone who's got Spark apps wants to run them in this confidential environment, reasonably confidential environment. Okay, and it would be interesting to port some of these others at some point. We've got another year of funding, so we're looking at 2 different directions. One would be what's the work needed for those? We probably won't do the work, but we'll document so that somebody can do it. And the other is what will happen on other processes where you might have some different way of doing enclave support. So how do we fit those together? And how do we talk to accelerators which don't currently have any enclave support as far as we can see, but maybe they have other ways they can be protected, who knows? Okay, the other work out there, Opaque, is just designed to hide patterns of memory access. It does oblivious memory, which is a very nice technique. Performance overhead, but it's pretty solid, but hasn't been done for Spark yet. And then VC3 is the Microsoft thing I mentioned, which is used for confidential cloud services. They have nice world in Microsoft and Azure because they control all the code for that. So they can even probably mitigate all the Spectre attacks on their code, which is, they're very good actually. really know what they're doing, which is good. But we're doing this slightly different task, which is taking Spark and putting it into SGX. And so basically, it's how do we do this with reasonable performance overhead? And the problem we have is the Spark memory footprint is just off-the-shelf Apache Spark uses a lot more memory than you have in Enclave. So you can't just go, load the SGX LKL, load libc, load Java, load Spark, and well, you can, and then watch the thing run 100 to 1,000 times slower than a normal world because it will be paging the whole time. So the trick is, can you put only the important bits of Spark in the enclave and leave the rest out, and just then, assuming you hardly ever call them, that might be sufficient. You may never call them. Maybe loads of code there that's just not used much at the time. Okay, so that's a kind of what's happened. You partition Spark is the main task at the moment. That's been done. This is done work now, about a couple of months back, and working. And you now have this, you need to move data between multiple JVMs, so we have to do some kind of mechanism for that. So there's a trick that Atamli here came up with, I think. He was the first guy saying, why don't you just use shared memory? And then we're like, how do we do that safely between, you can't do shared memory between the enclave and non-enclave. But we could implement an inter-process communication mechanism to do that efficiently and so on. Okay, this is just say the goal is to move a minimum amount of Spark code to the enclave. So there's a whole bunch of sort of startup stuff with RDDs. There's the actual map and the sort of sort of reduce steps that happen, and then the output results. So if you only move these pieces, the enclave, decrypt input data, iterate, encrypt the result, then, and you can do this over multiple threads, then you're done. And it's sort of weird. I don't quite understand why there's so much memory footprint for Spark, because this works. I mean, what's all the other code doing? Don't know. Mystery to me. I haven't gone through Apache Spark code and looked at what there is there. I'm sure it's got uses for other things. It's probably bookkeeping and other stuff, maybe debugging. Okay, so that's basically what I've said. So we're going to run out of time if I don't skip a bit. And then data movement between, the goal was to implement shared memory between the JVM, so you could have these different Spark tasks that you communicate efficiently, and you have to care about encrypting the right way and so on to make that safe. And then, done that. And there's this memory footprint where, well, this got garbled here a bit, excuse me, but basically, the default would be terrible, but by doing the partition the right way, we do manage to, so the SGX is down at 26 meg. Just doing the right bits of compressed versions of Java code from Spark and get that down to 50 meg, and that just about fits. Sorry about that. That slide is a bit, I don't know, it got mangled. Okay, so that's where we've got to. So we have this working. We're currently trying to find interesting problems running in Spark so we can try that. Selfishly speaking, this is a research project at the moment where we'd like to write a paper that convinces people. And if you write systems papers, this is a sort of lesson for people. All the top systems conferences hate you if you just do a paper exercise. They like it if you've got systems performance numbers, but they love you if you actually have a real example. If you say, we ran this on this bunch of data. We even tried these attacks and they failed. And, and it performed this much worse than running, native Spark on blah. And so we're kind of on the lookout for some nice, so if anyone's got a good example that preferably doesn't involve absolute requirement for confidentiality, because we're going to test this, and if we're wrong, we would breach the confidentiality. Of course, we'll test it in a secure data center or on a public cloud, but we'd still like to not have the guilt of getting it already wrong. So if somebody's got a reasonable scale problem they've got in this sort of world, that will be interesting. So it's a line of work. There are a relatively small number of people working on this at the moment. Sort of truth in advertising. In the security community, there are quite a few people do not trust SGX one bit. And to be fair, one of the main reasons is it's really complicated. I mean, you saw quite a few moving parts. So it involved processor change, memory controller changes, microcode changes. The Intel processor is incredibly complicated enough. And so when I say do not trust, it doesn't mean they think Intel is run by the NSA for evil reasons. It means it's so complicated, something's bound to be have a vulnerability of its own, in the same way that, if you remember 4 years ago, if you used TLS, which, HTTPS, there were something in the order of 60 bugs reported that involved vulnerabilities in 1 year, 2014. And that's just one relatively simple piece of code. This is the entire processor change, right? So what are the chances they haven't made any mistakes in there that somebody will uncover at some point and then render the whole thing maybe not very good? Demonstrably, as I said, the Imperial folks showed you can run Spectre across this and pull data out of the cache as a result of speculation. So that's itself a little bit worrying, but that you can mitigate in the ways that Spectre's mitigatable, which you heard about a couple of weeks back from Mark Handley. So we don't think that's the kiss of death. And we think that the value of this is to improve confidentiality. It's not, you never make claims that we are secure. You just say we've defended against those attacks better than before, probably. Okay, that's sort of, history says you will get embarrassed with high probability quite soon if you say this is all absolutely fine. That's not a good thing to say. The other interesting thing I think is, as I mentioned, we're going to compare this on other enclaves, other hardware support for enclaves. So there isn't just Intel in the world, there are more ARM processors in the world. Many of them support Trust Zone, and AMD have some pretty nice support for enclaves. It's quite different. The interfaces are not that different, so it's quite easy to make a port of a system so that it will work across the different hardware. And ARM stuff has been around 6-7 years, and nobody's broken it. That's pretty encouraging. It's quite a lot simpler, so there are different constraints going back to system design that you'd have to solve. And obviously ARM processors are not typically as fast typically, but there's no reason that would always be true. So there's a definite line of attack on this stuff that moving forward that makes some kind of sense. The one thing we are currently doing is, if you think about Spark or MapReduce style processing, the code is repeatedly running over data, it's iterating over data that's moving through the system and then being distributed, and then you go to the next stage of the iteration. So you have all these enclaves running the Spark code and running this, iterating this function over the data. But the data does not have to stay in the enclave terribly long. And side channel attacks require time. And so you could imagine some combination of that with some other technique to make a side channel attack not affordable. That's a bit of a reach, but you could also imagine the people building the new versions of the memory controllers for the encryption thinking about how you combine that maybe with hardware support for oblivious memory or some other technique. And then you might have something that would be quite hard to break, even with the smartest people. And really it's like the joke of people, I don't know how many people here cycle, but you only need a bike lock that's better than the next bike lock, because then people will go for the other bike. Or you need a bike that's worse than the next bike. Okay, so that's the other side of the equation. If your data is not financially valuable or politically interesting, then of course you're unlikely to be attacked. Or if you are, it's not so embarrassing. It's just sort of annoying. But in reality, the point of this is to try to raise the game for people, not just in the Turing, so that you can take things that really, there's a lot of low-hanging fruit if we could only do a lot more machine learning, model inferencing over healthcare data or financial data. There are so many things that could be, societally valuable, economically valuable, healthcare, all those things. But you need to persuade people that we're in a pretty good world in terms of confidentiality to let that be easily doable. Otherwise, the current, if you look at our relationship with NHS Scotland, the current ethical approval process is deliberately complicated, slow, because each person, you have to check you're a sane person, you're not going to do bad things, you are going to work with them for a particular healthcare reason, and so that's going to be the bottleneck in the system, right? It's a human, we were talking earlier about human bottleneck, and there's a very, very slow step to get approval to do some machine learning task over that data, for good reasons. If we can automate that somewhat, then we can do a lot more things. Okay, I'm done at that point. We have about 5 minutes for questions if there's any Q&A.